Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have José Rafael Fuentes with us today. Hello, Jose.
Hey Frank,
How you doing?
once again. I'm
Uh,
doing great actually.
Good, good. And it is April 14th of 2025 as we record this. And Rafael, what's your geolocation?
For now it's Boulder, Colorado,
Ooh,
but
so
in September I'm moving to Pasadena to Caltech actually as a postdoc.
very cool. Congrats.
Yeah,
That's nice.
thank you.
Very good. Yeah, and you got some awesome scribbles over your right shoulder there. I see all kinds of funny symbols.
Yeah, that is some seismology that we have been doing with Brad Heidman
Very
at CU Boulder. Yeah.
nice. Very cool. Good. Let's see. And is spring in the air in Boulder? Or are we still sort of in our winter mode or kind of in between?
It's a nice question because last week it was very hot, like every day. It was perfect, like sunny, blue sky, excellent. And yesterday, during the night, there was a bit of a snow. So today we woke up with the snow in the mountains. So kind of bipolar
Yeah,
a
yeah.
little bit.
It's spring. It's spring, right? Can't decide whether it's summer or winter yet. So
Yeah.
very
How
cool.
it how are things in Phoenix?
Yeah, last week was hot. We hit our first triple digit Fahrenheit last week. So probably when you were having your nice weather,
Wow.
got over 100 here. Uh,
Oh wow.
but it's cooled down a little bit, so we're sort of in the 80s to 90s right now, and so it's quite pleasant. So yeah,
Yeah, that, that is decent.
yeah, I don't mind it. And Jose, what do you like to do for research?
Oh, many things. I work on astrophysical fluids applied to many things that are round. In
Yearly
particular,
round. Yearly round.
yeah, nearly round. In particular, white dwarfs, more recently neutron stars, and giant planets.
Cool. There.
Yeah, all sorts of physical processes, dynamos, compositional mixing, convective boundary mixing, and a bit of seismology as well in the sun.
I was going to say we can add seismology to that, or see if we can pick up those deviations from spherical symmetry that way.
Yeah.
Cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy and go get one for free. 3D
Yeah.
simulations of semiconvection in spheres, turbulent mixing, and layer formation. And Jose, take us away.
Yeah, thanks for the nice introduction. So before having this chat with you over Zoom, I was thinking, what is a good way to start talking about this? And since I know that people that watch these videos are not always in our field, or even they can be like usual people going around on internet, I think it would be nice to start from the very basics. Okay, so that is what are we gonna do?
Do you want to bring up the extra figure?
No, not yet.
Okay.
So usually when we make models of stars and planets, we have to make assumptions. Uh, for example, we make assumptions of the internal structures of these objects, assumptions about the thermal stratification and the compositional stratification. And based on those assumptions, you can see how energy and mass will be transported within the fluid, within the interior of the star or the interior of the planet.
Okay.
Okay. Uh, Usually, you have situations where inside these objects is hotter in the deep interiors and much cooler near the surface, right?
Mhm.
And also the composition, it's mostly dominated by heavy elements near the center and more light elements near the surface. In stars, that is a common result of nuclear burning, for example.
Mhm.
You burn light elements, you create heavy elements, you release heat, you end up
Mhm.
having with a hot interior that is denser at the center, right?
Yes.
In planets, the situation is a bit different because we don't have nuclear burning inside planets. But in gas giants, for example, you can develop these thermal and compositional structures over time.
Okay.
For example, you can develop a thermal gradient by cooling down the planet to space from the surface, okay? And you have heat trapped from the formation of the planet, so it's natural to think about a thermal gradient, such as the fluid is hot as well in the interior, just like in stars.
Yes.
And you also have differentiation process that can create compositional gradients. In gas giants, you have this helium rain that separates from hydrogen that also contributes to a gradient in such a way that you have a mean molecular way that is larger near the center and much smaller near the top, right?
I'm with you.
Yeah. So based on those internal structures, you have to decide how you transport the energy and mass, as I said before. And you have two options in general. You either transport by conduction. It could be conduction, photon diffusion, microscopic diffusion of photons.
Yep.
Or you can have conduction of electrons, also microscopic processes. But what is most efficient at that are fluid motions, meaning convection. You move fluid motion from one place to another, you transport material, you transport energy.
Got it.
And how you decide between these two ways of transporting stuff, it very much depends on the internal structure that we have in our models, right?
Yes.
Usually, when you have a well-mixed object,
okay,
you can display in the usual way that we learn about convection. For example, in a well-mixed object, you displace a bubble of fluid elements from below, and if the thermal gradient is strong enough, you can ask, what is the temperature of this blob? Is it hotter than the surrounding? If it is hotter, it will just go up because it's less dense, and you will be convectively unstable, and you will drive convection, just like the water in your kitchen that is boiling, right?
Very good. Yes.
But when you have compositional gradients, things are different because usually chemical species diffuse much slower than temperature, than heat.
Yes.
So if you are in a situation where you have a gradient of mean molecular weight, let's say you have iron at the bottom and hydrogen at the top,
okay,
and you displace that bubble of fluid, you will ask the same question. Temperature hotter than the surrounding? Maybe it is, but that doesn't necessarily mean that the fluid parcel will be less dense than the surrounding, because it's coming from below.
Yes.
And it's retaining the original composition, the heavy elements. So you compare, maybe I'm hotter than the surrounding, but I'm heavier because the surrounding has hydrogen and the blob has iron, for example. So there is going to be a tendency to sink, like a restoring force.
Yes.
So that is why we say that in this situation, if you wanna develop convection in the fluid, what you need is to overcome the composition gradient as well, because composition tends to stabilize the fluid against convection. Yes. That is called the Leduc's criteria for convection.
I'm with you.
So that is one part of the story, but there are many situations in stars, in cold convective stars, let's say, and in giant planets in particular, where you can be thermally unstable, meaning that if there were no composition, the fluid can be convectively unstable.
Okay.
But at the same time, you can be compositionally stable, meaning that you are Churchill unstable to convection, but Leduc's is stable to convection.
Yes.
So the thermal stratification is still unstable, but the compositional gradient can inhibit thermal convection.
Yes.
Within the fluid body.
Yes.
And when you have that situation, that leads to a phenomenon that is called double diffusive convection. Yes. Or semiconvection, which is what are we going to talk about now?
Okay.
Okay. So this is important. I said for cold convective stars, you are burning light elements into heavy elements in their cores. So you are developing a composition gradient in the core that can maybe stabilize the fluid against thermal convection.
As one example. Yeah.
The other example is which I'm very interested into. It's in the core of the giant planets.
Okay.
We have observations from the Juno mission and measurements from the seismology in Cassini for Saturn and Juno for Jupiter, that the core of this planet is not a centrally condensed core, but instead is a dilute core, meaning that you have heavy elements immersed in a hydrogen helium envelope distributed in a non-uniform way.
Yes.
That is what it's called, like a fuzzy core or dilute core.
Okay.
It's a gradient of heavy elements that is coexistent with a thermal gradient inside the planet. So in those situations, you could develop these double diffusive instabilities, which have the characteristic that when you trigger them, you can enhance the transport properties in comparison to what you would expect from pure molecular diffusion.
Right.
The transport is still weaker than pure convection, but it's much larger than pure diffusion. So if you happen to have that in the interior of a star or a planet, we should account for it, because that will, again, modify the internal structure. And if you modify the internal structure, the cooling evolution of the system will change.
Yes.
So if you go to equation 1, so there are 3 parameters that govern the let's say that sets whether the instability will arise or not. Okay. One is the Prandtl number, which measures the ratio between the kinematic viscosity and the thermal diffusivity of the fluid. That is the Prandtl number. Yes. The other one is that parameter called tau in the middle, which is essentially the ratio between the chemical diffusivity and the thermal diffusivity.
Okay.
And the third parameter, which is probably the most important, is what is called the density ratio, which measures the ratio between the stabilizing effect of the composition gradient to the destabilizing effect of the thermal gradient. Okay. So all these parameters depend on the fluid properties, particularly the Prandtl number and the tau, the diffusivity ratio.
Yes.
Those are determined by microphysics, usually very small in stars, talking about 10 to the minus 6 or something. Impossible to run numerical simulations in that regime.
Yes.
But for planets, the Prandtl number and tau are about 10 to the minus 2 or so. So we can actually do numerical simulations. And if you are curious, for the Earth in the ocean, the Prandtl number is 7, and the tau parameter there it's very similar to what we believe it is in planets, about 10 to the minus 2 or so.
Yes.
So there are some analogs between oceans and fluids in gas giants.
Cool.
But the density ratio, it's more hard to characterize because it depends on the internal structure of the fluid, which we don't know a priori. But anyways, so if you go to equation 2.
Yes.
That is the result from the linear stability analysis. You have a fluid with some thermodynamic properties, Prandtl number, tau, thermal and compositional structures. And if this density ratio falls between 1 and that upper boundary there, Prandtl plus 1 divided by Prandtl plus tau, then you will excite the double diffusive instability. Whenever that ratio between the compositional to thermal stratification falls between 1 and that upper boundary, you excite the double diffusive instability.
Okay, cool.
If your density ratio is smaller than 1, that means that the thermal gradient is strong enough to overcome the composition gradient, so you will have just overturning convection, thermal convection, the usual one. And if the density ratio is larger than that upper boundary, then you just have waves. You are fully stable to convection. Nothing happens. All transport is by diffusion or sort of diffusion. But if you're in between, again, you have double diffusive instabilities. And what is interesting is that through numerical simulations in 3D, this is work done by Pascal Garraud at UC Santa Cruz and her group during like 10 years. Thanks to that really nice work, we have a good understanding of the double diffusive instability now, which brings us to I sent you beforehand. Yeah, if you can pull that up.
Oh, I'm sorry. You want the figure now?
Yeah, the figure.
Okay, we're going to bounce out of here for a second, folks, and we're going to put some bonus material in here.
This is bonus. That should
Bonus
be in the
material.
paper, but for some reason I didn't. So yeah, this is what I was talking about. This is a diagram as a function of the density ratio that tells you the different regimes that you can have depending on your microphysics and internal structure. So I said that between 1 and that upper boundary, you have double diffusive convection.
Okay.
But Pascal Garraud and her collaborators, using hydrodynamical simulations, they show that actually the double diffusive instability can manifest in two modes. One mode is called homogeneous oscillatory convection, where you actually have gravity waves that have a larger transport than pure molecular diffusion, but it's not that large. It's a modest enhancement, let's say. Some people call it turbulent diffusion.
Yes.
But it's just a modest enhancement of the transport.
Yes.
And if you are closer to 1, you can trigger something that is called layered convection, the layered mode of the double diffusive instability, which is the most interesting one, because what happens is that you spontaneously form this structure where you have multiple convective layers separated by thin interfaces where the transport is by molecular diffusion. So this is exactly the same to what we see in the Arctic Sea, for example. The double diffusive staircases where you have multiple convective layers, and it's the same to what you see in your coffee, in your latte, for example. You also get these layers that develop pretty much due to the same physical mechanism. It's double diffusive convection. Yeah, so it's milk, coffee, different diffusivities, different temperatures. If you are in the right regime, you can develop layers, and that is what you see. So we believe the same happens in stars and planets. As I said before, there has been a lot of work on this using Cartesian boxes without rotation.
Yes. Yes.
We have done a little bit, including rotation, also in Cartesian boxes, with rotation anti-aligned with the gravity.
Okay.
But in real systems, in planets and stars, they are not boxes, of course.
No, they're not.
So we should account for spherical geometry, and most importantly, we should account for spherical geometry because these systems are naturally rotating. Some of them rotate faster than others, of course. But when you have rotation in a sphere, the gravity and the rotation vector are misaligned as a function of latitude. So, and that can change things because the Coriolis force is going to change as a function of latitude.
Yes.
Buoyancy, the net buoyancy also change as a function of latitude because rotation do stuff to convection and semi-convection. So that is what we want to explore.
Cool.
If we happen, first of all, there is no work until mine, I think, that try to reproduce what in boxes, but on a spherical geometry. Okay. So I think it's this work is interesting because for the first time we are showing the formation of semi-convective layers in a sphere without and with rotation. So yeah, motivated by that, but by that geometry effect and how rotation affect the system when you have a spherical geometry, is that I ended working on this really nice problem. So what I did was basically I took a sphere, I used Daedalus, the spectral code Daedalus, and I initialized the sphere with a thermal gradient and a compositional gradient.
Okay.
In principle, I don't know if all the stuff that was done for the boxes will work on the sphere. But as a guess, I put parameters that I knew that they are gonna show layers in the boxes.
Okay.
So I picked a good guess, and I put, okay, I will put the same parameters, exactly the same values,
Sure.
and see if I will get layers or not. So I'm interested in the layer regime because that is the regime that has most of the transport, the most interesting one.
Yes.
For these objects.
Very cool. Okay.
So I pick up some values. I saw Boolean S equations just for simplicity because it's really hard to go compressible with these systems.
Okay, so it's
I use Dedalus and I vary. I run two kind of simulations. One set of simulations where I vary the degree of stratification, increasing the stability, meaning that I move the density ratio parameter that controls where you are gonna be across that diagram, across that parameter space, from values near to 1 and I think to values near 2.
Okay.
Without rotation. Okay. And then I run another suite of simulations where I fix that value of the density ratio to something that will develop layers.
Okay.
And then I increase the level of rotation by changing the Rossby number, increasing the rotation rate, and see how that affects the transport properties and everything.
I'm with you.
Okay.
Yep.
Okay. So actually we have figure 1 there, which is a canonical case that has a density ratio of 1.25.
Okay.
Which I knew it was going to develop layers in the boxes for the microphysics that I have in the simulations. And it happened to also develop layers in the sphere, and actually in a very similar fashion. You start with what you are seeing here is the density field, I guess. Okay. I think.
Yes.
So just at time equals 0, you have these gradients in the density, the initial gradients. And since we are in a situation where we expect to develop the double diffusive instability, then after some time, you can see that the fluid transitions into multiple layers, multiple convective layers separated by diffusive interfaces. Yeah. I think in that we have like 3, different colors and not the different compositions. So
yes,
you have a core that naturally develops in the simulations, because there is no inner boundary there. So it's this is really neat. We don't need to impose like an inner boundary. This is not on a shell. This includes the full spherical space. Cool. And what happens later is that as the system evolves, you can see that from 0.03 to 0.06, like panel C, you lose the inner layer. So they mix.
Okay.
What is happening is that the outer layers start to entrain the
richer stuff.
The layers that are below. They engulf, and in the end, if you wait long enough, you are gonna end it with a fully convective sphere that is well mixed. So if you see panel E, that shows some radial profiles, and I shifted them over time so we can see them more clearly. So if we take a profile to one of those snapshots where there are layers, you can see that whenever you have a vertical line, that means that the density or the composition is constant. So that is a well-mixed convection zone. Then you have an interface where it's these rather horizontal lines. Then it becomes vertical again, then an interface and vertical again. So those are the staircases profiles that people talk about.
Got it.
Okay. And in the end, by the end of the simulation, everything is going to be flat. It's well mixed. Yes. And we will discuss about that because it's important to decide whether this is relevant for the evolution of these objects or not. But let's keep that for the end. So that was for one density ratio. So if you go to figure 2, I think. Yeah. Let's go to figure 2.
Some of that. These results for non-rotating simulations.
So figure 2. That is better. Okay. So in figure 2, the same, some snapshots of the density, but this time for different stratifications. So I'm increasing the strength of the composition gradients
Yes.
from 1.25 to 2, basically.
Yes.
And again, you see layers in all of them. But what happened is that as you increase the level of stabilization by the composition gradient, meaning if you increase the rho parameter, this density ratio, that means that the composition gradient becomes sharp enough to kind of the thermal convection to go through the interface, basically.
Yes.
So you can see that the layers are more well-defined for the case rho equals 2 than 1.25. Yeah, that is because the composition gradient is strong enough to fight for a bit against the convection.
Fight against it. There we go. Very cool.
Yeah. Okay. But again, you wait long enough, and you wait long enough, and the fluid motions will end mixing everything in the end.
Okay.
Yeah, well mixed. So this is not new. This is something that we knew that from the simulations in boxes, and it seems that the same is happening in the sphere. So at least for non-rotating cases, the dynamics is pretty much the same.
Okay.
You can start with your favorite stratification that will give you the layers, but it doesn't matter. They will just mix.
Okay.
So
that's good.
One of the things. Okay. So if we go now to, let's go to figure, the one that is in front of that one. I think that is figure 3. Yeah. And let's look at the panel B, actually.
Okay.
Panel B. Yeah, let's look to panel B. So in panel B, what I'm plotting there, it's the ratio of the Nusselt numbers as a function of the density ratio. The Nusselt numbers is just a way of measuring the transport properties, okay?
Okay.
The transport properties. Just think about that. And I measured that for different simulations, and I put some lines in there. So you see prediction there, different predictions. One is from Toby Wood, 2013, where it predicts a transport that is constant across any internal stratification. There is also a prediction by Erika Rosenblum from 2011, which is that the dashed line in there, or how the transport change as a function of the density ratio again.
Yeah.
And there is also a prediction by Henk Sprout from 2013.
Yes.
Which, if you think about it, you will say, oh, Sprout is right. I mean, Henk Sprout predicted the same, the prediction from Henk Sprout for the internal transport is consistent with the simulation, which is true. But if you look at the scale, it's just a factor of 2 from,
I was going to say from Rosenblum.
From America. It's just a factor of 2. So we should be honest and say, I mean, if I scale Erika's prediction by some factor, it could be consistent as well. I mean, it has the right slope as a function of the density ratio. So it's just a prefactor that could very well depend on the geometry of your system. So
fair.
So fair. So if we go down, we go down, I think, just to show the equations. So equation 10, let's look at equation 10 and 11. So equation 10 is the prediction by Henk Sprout.
Okay.
So it's a factor Q there. It's a constant of order unity, which I set to 1 in this line, divided by the density ratio and this diffusivity ratio to the 1/2. Okay.
Yes. Okay, I'm with you.
Yeah. And in Erika Rosenblum's prediction, which is equation 11.
Yes.
It's 1 over rho, rho, just like in Henk Sprout. That is why the slope is correct.
Yes, you got.
But the prefactor is 1 over tau, and that can change. I mean, I can scale Q to something,
anything,
just to make the data agree. And so I don't think we are in a stage where we can say one model is better than the other. That is my recollection.
Yeah.
And equation 12, which is Toby Wood's prediction, that is a bit off because that predicts a constant transport, and we don't see that at all.
Yeah.
And it also depends on prefactors B and A that are measured from the numerical simulation. So yeah, so I think that to test the Toby Wood's prediction, it's more complicated. But in any event, the message from this first suite of simulations without rotation is that the double diffusive instability, the dynamics of the layers, and the transport properties, like quantification of the fluxes, etc., it's pretty much the same or changed very little with respect to previous work done on Cartesian boxes. Okay,
good.
So there's a good agreement. It's really nice. But real system rotates, so let's see what happens when you put in some rotation to it. So let's go down. I think we're gonna skip figure 4, but I can say pretty much that gamma minus to the -1.
Yes.
It's something that is called the buoyancy flux ratio.
Yeah.
Which is an important parameter for double diffusive convection. It measures the composition flux to the heat flux, basically. And yeah, we calculated that, and it lies between the expected values. So nothing fancy, nothing wrong. It has to be less than 1, and close to 0.5 for the microphysics that we have. So that is another check for a comparison with the Cartesian boxes. It's
good.
It's very similar to previous work. So yeah, nothing wrong for that.
Okay.
But when you put some rotation, things become interesting, and let me explain here a little bit why. When you put in some rotation, you add the Coriolis force, right?
Yes.
Acting on the fluid, and what happens is that when rotation is strong enough, you can change the morphology of the fluid motion. When you have convection, rather than having like convective cells that are very symmetric and isotropic, when you put rotation, and in particular strong rotation, you can reach into the Taylor-Feldman effect, where rather than having these cells, you develop columns.
Cool.
So the fluid becomes 2D, and you end up developing like these, like tornadoes, basically.
Yes.
that are vertically invariant.
Okay.
So if you change the morphology of the flow, you will expect to change the heat transport, the mixing, the level of mixing, because it's just the geometry is different. It's more like a 2D motion rather than a fully 3D turbulent. So
interesting.
Things change, and we know from studies of thermal convection in the fluid dynamics community that is well known by Chandrasekhar, actually, since Chandrasekhar's time, that rotation tends to inhibit convection. Just like a composition gradient, rotation tends to stabilize the fluid against convection. It gets harder to excite convection when you have a strong rotation. And if you develop convection in a rotating flow, the transport is also much smaller. It's weaker. It's weaker. Okay. It's particularly the radial transport, because you are not doing this. Instead, you are moving like it's more horizontally rather than vertically. So the radial transport is weaker. So that is for thermal convection, but we know speed of semiconvection and double diffusive convection under the effect of rotation when you have gravity and rotation like this, like at the poles, if you can think about it.
Okay.
But now we have this misalignment between gravity and rotation as a function of latitude. So we want to check that. We want to understand and see what happened. Okay. Again, I don't think this has been shown before in previous studies.
Right.
So I believe this is the first study that actually shows what happened when you have all these effects.
I agree.
So
let's chose this article.
So let's go to that figure. Excellent. So
out a little bit so we get it all. You can get the global picture, and we'll zoom in as we go. Okay.
Oh, but first, I think I would like to mention the Rossby number. So can we go a little bit up?
Yep, sure.
Yeah. So the way that we quantify convection in the simulations is through this dimensionless number that is called convective Rossby number, which is essentially the ratio between the rotation period to the free fall time scale of the convection. So if the Rossby number is small, that means that rotation happens on a much faster time scale than the turnover time scale, okay? And convective Rossby numbers of 1 or larger means that rotation happens on a slower time scale than convection.
Okay.
So when we talk about rotationally constrained turbulence or rotationally constrained convection, means Rossby numbers that are smaller than 1. Usually.
Okay.
Okay. Okay. So now we can go to the figure. Okay. Because I run simulations for different convective Rossby numbers.
4 different ones.
Yeah, 4.
Here we go.
I apologize for not running simulations at a different density ratios, but these simulations are very expensive. So that is why I decided to keep the density ratio fixed to 1.25, but I moved in the rotationally constrained space. Let's see. Okay. So in that figure, I'm showing again snapshots of the density field for convective Rossby numbers of 1.5 and 0.25. So the difference in the morphology of the flow it's quite evident.
Yeah.
Of 1, it's very similar to the non-rotating case. You can see layers. There is a lot of shear now because you induce also differential rotation and all sorts of things. So there is a lot of shear that distorts the layers a little bit. And you keep increasing the rotation to the right in this plot. And you can see that the morphology of the flow started to change. In particular, if you compare panel B with panel C, it's very different.
Very different. Okay.
Or panel A with panel C. That is more extreme, actually. You can see columns. You can clearly see columns like elongated structures with horizontal scales that are much smaller than the vertical ones, particularly near the poles. At high latitude.
Yes.
And if you go to the equator, that is actually more similar to what you see in a non-rotating system. Like there is like a clear separation of different compositions. You can see layers. You can see vortices too, just like what you were showing in that. Yeah, that is a clear vortex.
Yes.
And in addition to that, the level of mixing that you get between the poles and at the equator seems to be different, actually.
Sure.
So if we look at panel D shows the time evolution. It's a meridional slice, theta and radius at different times.
Okay.
And it seems that you have more mixing in the equator rather than at the poles, right? You can see that the convective, one of the convective layers it's thicker near the equator than at the pole. That is more clear for time equals 0.1, right?
Yes.
It's kind of
very clear here. Yes.
Yeah. So that means that the morphology of the flow is that the morphology of this semiconvective layers is not spherically symmetric.
It shouldn't be, right?
Yeah, it shouldn't be. So that is important because that means you work on 1D evolution models that are spherically symmetric. So how we account for that when we include these different physics?
Okay.
So yeah, it's an interesting question, and I don't have the answer. Okay. Okay. So we have a difference in the morphology of the flow. We see the formation of layers, but the morphology is different. So that is a check. Let's go then to the next figure, which I think it shows the radial transport. Let's see.
Okay, 6.
No, it's not that one.
Okay.
Is that one?
Volume averages, figure 5.
Oh yeah, exactly. Yeah, figure 5.
Yeah.
Okay. So in figure 5, we have again the Nusselt numbers, which measured the transport again. It's how efficient is the convective transport or turbulent transport respect to diffusion. It's basically that. And as you can see, that as you increase the rotation, this radial transport gets smaller. So I measured compositional transport in the solid lines and the thermal transport in the dotted lines. So if you go from dark blue to light blue, that means we are increasing the rotation in that direction. And you can see clearly that rotation is also affecting the internal transport for these semiconvective layers.
Both composition and thermal. They both.
Yeah, both. So that is interesting because that means again that rotation acts in a similar way to composition gradients. Actually, they tend to stabilize the fluid against convection, reducing the transport.
Yes.
In panel B is the buoyancy flux ratio, which again it's much smaller than the non-rotating case, like by a factor of 2, I would say.
Yes.
Yeah, the non-rotating case is the dark blue. Yeah.
Okay.
Yeah. Okay.
Now it's got a longer tail there.
Yeah, and all of them converge to a constant that is the equilibrium state set by the boundary condition. So that is not relevant. That happens when the whole thing is fully mixed. What is interesting is what happens when you have the layers, which is before they reach this steady state. And clearly the transport is much smaller, again, in the rotating cases.
Yes, that is clear.
Cool. Yeah. So if we go to figure, I think it's figure 6, the one that is
6
after
3Ds, I think 7.
Yeah, 7. Yeah. So this is an interesting one because when I saw that there was more mixing at the equator than at the poles, I realized, well, let's check instead of the having measuring the transport like over the whole sphere, let's look at how the transport change as a function of latitude, basically.
Yes.
And this is what this plot shows. On the vertical axis is the colatitude, and the horizontal axis is the Nusselt number, which is normalized to the maximum.
Okay.
Again, dotted points are thermal transports, and the solid lines are the compositional transport.
Okay, just like
and for different Raspberry numbers. So this is normalized, so we will not see the differences between the Raspberry numbers. That is fine. But what is interesting here is that in the rotating cases, the flux is larger at the equator. This is a colatitude of 90 degrees. Okay?
Right here.
And if you go to the poles, the fluid has a smaller transport. So this is consistent with the snapshot that I showed you in the previous figure. We are seeing that the convection zone is thicker near the equator because the flux is larger there. So I was at the IPAM conference. I think that happened late January at UCLA.
Okay.
We were discussing about rotating convection a lot. Actually, it was a workshop about rotating convection, and I brought this up. Like, is there a reason for why the transport in rotating convection tends to be stronger near the equator and much smaller near the poles? And it turns out that things are more complicated than when I thought.
Okay.
And there is a parameter in fluid dynamics that is called supercriticality.
Okay. Yes.
Which essentially measures how vigorous is convection in a rotating system. And it seems that it's normal to have a much stronger flow in the equator than at the poles for moderated supercriticalities.
Okay.
But if you go to more extreme parameters, like more vigorous convection, you can actually revert that behavior and maybe have more flux coming out from the poles. And if you go even beyond that, you can go to Rossby numbers that are way larger than 1, and everything becomes like isotropic, very similar to non-rotating.
Yes. Okay.
So I realized that my simulations were in a regime where we have a lot of turbulence, but it's in the regime where it's expected to have more flux coming from the equator.
Okay.
Yeah. So it's complicated, unfortunately. But in any event, with these simulations, we were able to confirm that layers do form in the sphere. That is one thing. In the non-rotating cases behave very similar to what we know from boxes.
That's important.
And when you put in rotation, we have shown, I think for the first time, that layers can develop actually for the same parameters that layers are seen in non-rotating system. You put the same parameters, you can also develop layers. And the morphology of these layers is different. Okay, it's more cylindrical mixing than spherical mixing. Okay, that is another difference.
Yes. Non-rotating.
Right. Another difference is that in the rotating cases, the transport is much weaker than without rotation, and that is consistent with what we know for pure thermal convection and not double diffusive convection. So the same, rotation weakens the transport.
Yes.
And the other difference, which is something that I didn't mention before, but I just remember about it, is that the layers survive for a longer time. You develop layers.
Okay.
In cases they mix quickly, as we saw before. But when you put in some rotation,
it lasts longer.
Because rotation weakens the convective transport, so the time scale of the layers merger is longer. It's much longer.
Okay.
So now this brings us to how we can apply this, or are these simulations important for these systems that I motivated before, like the stars and planets?
Right.
I think that for stars, the energy source in the core is too large. So even if you have rotation, these layers can easily mix.
Okay.
There is some nice work done by Evan Anders from 2022, I think, Schwarzschild-Leduc criterion. It's an AAS letter where they actually show that the semiconvective regions do not survive for a long time.
Okay.
I think that is true. But in planets, in giant planets, we have evidence from seismology and from the gravity that the interior of these objects are not fully mixed. So if there is semiconvection happening in the gas giants, in Jupiter or Saturn, for example, these layers are there.
Cool.
You can either be in a state where you don't have layers, let's say just a stable stratification, or you can have a semiconvective diode core with many layers.
Okay.
So in gas giants, there must be something that is preventing these layers to mix. One possibility could be rotation.
For example?
So I wrote an AAS letter last year characterizing the time scale of the mixing of these layers when you have rotation using Cartesian boxes.
Yes.
And what I found is that rotation can delay the merger of the layers by about 2 to 3 orders of magnitude, because these systems rotate really fast. I mean, Jupiter rotates once every 8 hours or 9 hours.
Yeah.
So Rossby numbers are really, really small, like 10 to minus 6 or something. Even when the layer thickness it's small near the core, maybe. So these are effects that should be taken into account, and they can help to explain why the subjects are not fully mixed. So that is one thing. And the other thing, I will leave that for towards the end. Because we can't test this with observations. So I think that what I think is that if we want to understand stars and planets, the evolution of these objects, particularly the ones where we expect them to have this sort of layers and semiconvection, we really need to characterize the transport and implement that in models like MESA or any other evolution code. But I think that we are very far from that, because if you want to characterize the transport, you need to have a good model for that, for how is the transport across the layers. And as you can see, these layers mix very fast, at least in non-rotating systems.
Right.
So we don't know the size of the layers precisely.
Okay.
So making a transport prescription for MESA, for example, it's really complicated. I know there are, but they rely on assuming some layer size, which is nothing different than an MLT prescription. So I think we need to better characterize those prescription, investigate how, under which condition, maybe layers get reach a steady state where they don't merge anymore. But so far, with the numerical simulations that we have in the literature, like until now, layers always merge. Could be a limitation because we are using incompressible models like Boussinesq, assuming small density variations in the fluid. So I think next step is going beyond Boussinesq at compressibility. That will give a natural tendency for the layers to separate because you will have many density scale heights, right? So maybe denser layers they don't want to mix with the lighter ones or less dense ones. So maybe that is a way to prevent these layers to merge. But so far there are no simulations of semi-convective layers adding density stratification. So that is the next step.
Cool.
Once we understand that, then we can maybe make prescriptions for 1D models.
Yes.
So yeah, that is what I have to say. I hope you enjoy this discussion. It's definitely an interesting topic, and I look forward to what comes next.
Well, I thoroughly enjoyed this topic because nobody has done this kind of stuff in full 3D before. So I think it's very cool. Very nice.
Yeah.
Yeah.
And it was my first solo paper.
Yeah, I was going to say, because there are not a lot of solo papers these days, right? They were much more common a long time ago.
I wanted to see what can I do on my own, but it turns out I think that it's better to have like papers with many collaborators because they can proofread, they can give you more suggestions for analysis, for discussion.
Right.
But yeah, I'm really happy with this paper anyways because it's something that I wanted to do, and it's like a close story for my PhD because I did my PhD working on this sort of topic, double diffusive convection, but in 2D Cartesian in salty water. So after 3 years since my PhD, being able to do this sort of thing, it's I feel proud.
Good. That's awesome. I'm proud for you. So asking, you were talking about it a little bit there toward the end. And so just sort of next immediate steps. You mentioned certain possibilities of, where simulations could go, and it will be a little while before, we encapsulate these 3D effects to capture it in some model for 1D. But how about the next set of 3D simulations? Where do you think we go with that on this topic?
I think with the next 3D set of simulations, what we need is, as I said before, a density stratification. That is a must step, Fluids even when the interior of these objects, the flows are very subsonic. The velocities are not that large. That is true. And the density scale heights are comparable to the radius. So you may think, Boussinesq is not that bad. But there are different considerations. When you have density stratification, you have different energy requirements for mixing because potential energy related to transport material will change, right?
Yes.
There are different requirements. In Boussinesq, you mix to a constant density, but in a stratified system, you mix to the adiabatic gradient. So the energy requirements are different. The kinetic energy flux is also different because you have asymmetry in the flows. So the cold flows that are going down are narrow and fast, and the hot flows that are going up are slower and wider. And that is a requirement of mass conservation because the density is different. So if you want to transport the same mass when you have low density, you need to go fast, right? If you go down, you go fast, but if you go up, you go slow. because the density is larger. So it's there are many things that can change everything when you add density stratification.
Okay.
So I think the next step, and I really hope the community, the fluid side of the community, work on in the near future is to go beyond to go beyond Bosinesque.
Yes.
I think that is the next step.
Very
And
cool.
only that, as I said, will be able to give you good prescriptions for Mesa.
Cool.
Uh,
Very good.
yeah.
Well, I like them both, whether it's 3D, a priori, or whether it's a 1D.
Yeah.
It's all perfectly great with me. So, very cool.
Yeah.
Jose, I want to thank you so much for walking us through your very awesome, first of a kind, unique article. Very nice.
Thanks for inviting me. I'm happy to chat whenever you want.
Sure. Okay. And that'll do. And everyone, and I hope this made your astronomy day, your fluid day, just a little bit better. And we will see you on the next one. Bye-bye.